We are set today to do our last section of chapter 9, and then Wednesday we will do section 10.1, and then Friday we'll review and test Monday, a week from today.
I love tests on Monday.
Especially Monday right before Thanksgiving break, right? So, before we go into today's section, any questions on type 1, type 2 errors? How many people have already done the homework over this section?
Over this one or type errors?
Over type 1, type 2 errors. Got it? Okay, most of you have not. Those of you that have done it, anything that was a little bit confusing?
There was only 3 questions.
Yeah, I think they didn't give me very many to choose from on this section. I hate giving a homework assignment with only 3 questions. That just bothers me.
I liked it. Me too. Did you get all of them? 10%.
So I'll tell you what. Here's let me zoom this up so it's a little bit bigger and a little bit easier to read. This is an example of a. This is either the review. Yeah, this is the review exam you'll get, but I've got some others I want you to look at that are off of last semester's 3rd exam that we'll look at. This is a type 1, type 2 error question. So if you think you got this down, read this problem and see how you do. Suppose 2 labs working independently measure water samples for the level of a toxic chemical. Lab A collected 150 samples, Lab B collected 15 samples. Both labs obtained exactly the same sample mean and sample standard deviation. It's not realistic, but suppose that happened. Both labs did all their work accurately and both used a .05 level of significance to test if the true mean is greater than the acceptable limit. Yet Lab B did not conclude the levels were too high, while Lab A did. Clearly, one of the labs has made the wrong conclusion, making either a type 1 or a type 2 error. Which lab is most likely to be the one in error, and which type of error would they have made?
So the null would be that the true mean is the acceptable limit.
Right. So the null hypothesis would be that the mean is whatever the limit is, and it doesn't tell us. So let's say the limit is 500. So this is the EPA upper limit. That's legal or safe. Right? The alternative is what?
Greater than 500.
Greater than 500. It's not safe. Okay? Which study do you think is the one that made the mistake? And then which type of mistake would that have been?
Lab B failed to reject the null.
Lab B failed to reject the null. That's right. Lab A rejected the null. It says Lab B did not conclude levels were too high, while Lab A did. So Lab B failed to reject the null. Lab A rejected the null. Which one do you trust? Lab A. How come? Bigger sample size, right? They had 150 samples. Lab B had 15 samples, so they had 10 times the evidence, right? Remember, hypothesis testing is evidence. We have sufficient evidence or we don't. So Lab B did not have sufficient evidence to conclude. They are most likely the one that made a mistake. So now, which mistake did they make? Type 1 or type 2?
Type 2.
That would be a type 2 error. Failing to reject the null when the null is false. And we don't know for sure the null is false, but Lab A, who did a better study, says it's false. So I trust that it must be false. Okay? Well, let me scroll that one down. This is also, no, I'm sorry, that's not a type 1, type 2 type. I'm going to come back to this one later in the hour. Let me look on this one. There was one more. No, I guess that's it for type 1, type 2 errors. The other two of these I want to show later in the class when I get to some of the topics in section 9.5. But that's an example of a test question that I could make out of type 1, type 2 errors that's not quite as straightforward or simple as some of the online homework ones are. So, any other questions over type 1, type 2 errors? All right, then section 9.5 is titled, let's see, limitations of significance tests. So limitations. That means, in other words, significance tests are great, but they're not always reliable. They have limitations, right? So sometimes the conclusions you can make aren't as strong as what you want to make. So the first one, what I'm going to do is just kind of go through the section and list the things that he talks about, and then we'll give some discussion about it. I won't be writing a lot of things on the board today, but we're going to do a few more example problems. The first one says that statistical significance is not the same thing as practical significance. What the heck does that mean? Well, what is statistical significance?
Data shows it's significant.
Okay, what do you mean by significant?
Well, less than alpha.
Okay, the p-value is less than alpha, so then it's statistically significant. And what does the author use as a definition of statistical significance? Well, let me make up an example here, and then I think that'll make it easier. Let's say that I'm doing a clinical trial, and I want to test to see if my new cholesterol medicine lowers cholesterol. Okay? So the change in cholesterol would be positive. You get a positive change in cholesterol. Okay? So I'm testing the null hypothesis that the mean, and I'm going to put a little d for difference, right? Mean difference in your cholesterol from before the study to after the study. So mean change. What would the null hypothesis be? 0. My null is none, right? No change. So the null hypothesis would be that the mean is 0. The alternative would be that the mean is greater than 0. Because I want to show that I had a positive change. Okay? So I conduct my study and I get a p-value of 0.0133. What's the conclusion? Okay, reject the null and decide that the data support, we have sufficient evidence to support that the cholesterol medicine works. That's what I was wanting. You got to say it in the context of the problem, right? So we're saying the alternative is true. And the alternative means that the average change is positive. So this medicine works, right? Is that everything you need to know? If you're a physician, would you start prescribing this drug based on that? What else do you need to know?
Side effects.
Okay, yeah, side effects and all that, but just about the effect on cholesterol. Okay, all these things, you said dosage, and that's true, but that's not what I'm after.
You know that it affects you enough. If it affects you a little, but you know that it affects you enough to make a difference.
Okay, that's it. Does it affect you enough to make a real difference in your life? That's practical significance. This says it is statistically significant, which means that the average change that we observed is bigger than you would expect just by random chance. Right? That's what a p-value tells us. How likely is this data to have occurred just by random chance if the null is true? Right? and it's not very likely to have occurred by random chance, so it's statistically significant. But what if I told you that x bar sub d, the average difference in my sample, was 2? Now cholesterol, you maybe need to know a little bit about cholesterol, but what's an average cholesterol for somebody? Does anybody know what level of cholesterol is considered unhealthy? What they call too high, and then they start trying to lower it? Over 200. If you get a cholesterol over 200, then they start worrying about it, and they usually, if it's right around 200, they use diet and exercise. If it gets up around 300, they'll start giving drugs, Lipitor and things like that, to try to drop it, right? Well, what if I told you that on average, my drug can drop it 2 points? Woohoo! Hey, it's statistically significant. But who's going to prescribe it and drop you from 300 to 298? Right? It's not practically significant. So that's the point. Is statistical tests tell you whether if it's due to random chance or not, or if there's really something going on, but it doesn't mean that that something is really worth worrying about. So you need both. You need something that is practically significant, but also shows up statistically significant. Okay? The next point is significance tests are useful, but not as useful as a confidence interval. What information does a confidence interval give you that a hypothesis test does not give you?
All the plausible values.
All the plausible values, right? So suppose I did this study and I come up with a confidence interval and it goes from, forget my non-practical significance, so let me get rid of that. Let's say it had something that was meaningful, like x bar equal 50, and I get a confidence interval of 58 to 88, something like that. From that confidence interval, I get a range of values where we think the true change in cholesterol is going to fall. Right? But I also get this piece of information. Now, I cannot get exactly what the p-value is, but I can get that it is significant or not. Would I reject the null hypothesis based on this? Yeah. How come?
It's not within
Because the null hypothesis is not plausible. It's not in there. If it's not plausible, then reject it. So my p-value would be bigger than or less than 0.05.
that.
Be less than. It has to make the same decision. The hypothesis test can be done by means of a confidence interval, but not the other way around. If I tell you the p-value from a hypothesis test, you cannot tell me what the confidence interval is. So the confidence interval gives you all the information that the p-value gives you, but it gives you more. It gives you plausible range for the true value. Okay? Now, I have to be a little bit careful here with one-tailed tests. By definition, the confidence interval is a two-tailed test, right? So in order to make it match, I'd have to fiddle with the confidence level and the alpha level, and then be a little bit different. So let's talk about doing two-tailed tests so that there is a one-to-one correspondence between the results of a hypothesis test and the confidence interval. Two-tailed test, two-tailed confidence interval. We said this confidence interval would have p-value less than 0.05. What would this confidence interval have? What would the p-value be? It would be greater than 0.05, right? What would this one be? Oh, wait a minute. This one wouldn't be greater than, because my null hypothesis is 0, right? So I wanted -2, right? Now the p-value would be greater than 0.05. I was thinking 50, so I wrote 48, because I said the word 50 when I wrote that. But so this p-value would be greater than 0.05. And again, how do I know? Well, because this tells me that 0 is plausible, so I'm not going to reject the null hypothesis. And if my p-value was less than 0.05, I would reject. The p-value and the confidence interval have to make the same conclusion. Right? There's a one-to-one correspondence. What about this? What would the p-value be there?
Still greater than 0.05? Still possible? Not equal?
It'd be right at the boundary of 0.05. Now, technically, this is an open interval. So what Delaney said is right. It's saying that anything between 0 and 88 is plausible, and 0 technically is not in this interval. 0.0000 with 1,000 zeros and 1 is in this interval, but 0 is not. Right? So the p-value would be slightly bigger, but I'm just saying it's going to be equal. 0, the interval, when the interval overlaps 0, that's when the p-value switches from being less than 0.05 to being greater than 0.05 at that 0. Okay. Here's an example from a previous exam. Of a test question getting at the same issue. Let me make that a little bit bigger. Right here. I want you to write down on your paper what the correct answer is to that. And I'm going to come around and look at your paper. Number 4. I'll read it out loud. When estimating a population proportion, you get a 95% confidence interval of 0.52 to 0.56. Which of the following statements would be true regarding the p-value of a two-tailed hypothesis test of the null hypothesis p equal 0.5? And then option A says the p-value would be less than 0.05. Option B says the p-value would be greater than 0.05. C says the p-value would be equal to 0.137. And D says there's not enough information to tell. Write down what the right answer is to that. And I'm going to come around and look at what you wrote down. And those of you watching on video, write it down. Write down what you think the answer is. So far I've seen nobody write anything down. You got an answer yet? Okay, that is not correct. What did you write down? Is it A? That is correct. What did you write down? Still thinking. Okay, that is correct. Not correct. Correct? Correct? You said that, right?
Yes.
Okay, that's correct. Correct. Good. Okay, it looks like we're hitting a little better than 50%. Okay, that's correct. We'll say the same thing? Yep, that's right. Okay, we're quite a bit better than 50%. The answer is A. The p-value would be less than 0.05. Now remember, the p-value has to lead you to the same conclusion that the confidence interval does. Does the confidence interval say that the null hypothesis should be rejected or that you cannot reject it? It says to reject it. The confidence interval goes from 0.52 to 0.56. The null hypothesis of 0.50 is not in that interval. Therefore, the interval says the null is not plausible, rejected. So the p-value should also lead you to reject the null, which means your p-value must be less than the significance level. Now notice that this significance level matches with this confidence level. 95% confidence is synonymous with alpha equal 0.05. What would a 99% interval be synonymous with? 0.01, right? It's the leftover percent. Let me see if I can find, I have another test question that I really like. I gotta see if I can find it. I found it. There, that's it. Suppose the study is conducted in a two-tailed hypothesis test of a null hypothesis that the true mean is equal to 4 has a p-value of 0.049. So here's the null hypothesis. The mean is equal to 4 against the alternative that the mean is not equal to 4. Which of the following statements would be true regarding a confidence interval computed for the mean of the population? A says a 95% confidence interval would exclude the number 4, but a 99% confidence interval would contain the number 4. Then B switches it around. A 99% interval would exclude 4, but 95% interval would contain it. C says both 99 and 95 would exclude. D says both would include or contain the number 4. And then E is always the fail-safe. Not enough information. Can't tell. And it's not that. Write down your answer. It's not E. Sometimes students want a part F. I don't have a clue. But you can't select that one. These things are horribly confusing when you just read them like, what is that trying to say? But just think about it. Think about confidence interval in relation to null hypothesis. This one is the exact same question you just did, but worded the other way. This time they give you the p-value and ask you about an interval, instead of giving you an interval and asking you about the p-value. But the relationship is the same. Well, okay. What did you write down?
Nothing.
Well, good. That is correct. That's your answer? Okay. That's not correct. That's not correct. Not correct. Got an answer? Oh, you're taking a mulligan? Mulligan, you get to try again. Do it exactly the same way as you did the last one. And I know that doesn't sound very satisfying to hear, but think about it from that same perspective. Okay, not correct. What'd you get? B, not correct. What'd you put? Okay, that's correct. Okay, good. Bad? No, I wasn't saying bad to you.
No.
You're correct. Okay, correct answer? A. Okay, Morgan went, what? Okay, think about it. Here's my null hypothesis. The mean is 4, right? If I do a 95% confidence interval, that's analogous to a significance level of 0.05. Would I reject, or, yeah, that's what I want to say. Would I reject this null at the alpha equal 0.05 level? Yes, because the p-value is 0.049, right? So the p-value is less than 0.05. So let me write it this way. P-val less than alpha equal 0.05. Okay? So a 95% confidence interval goes along with the 0.05 significance. So this must make the same conclusion. What's the conclusion here? Reject. So this has to reject 4 as being plausible. So it would not contain 4. So let's say it would go 4.5 to 6.5, something like that. It would not contain 4. But what about 99%? Well, that's analogous to alpha equal 0.01. Is the p-value less than 0.01? No, they didn't change the p-value. The p-value is still 0.049. So the p-value is greater than alpha equal 0.01. Therefore, a 99% confidence interval must fail to reject the null. It must say 4 is plausible. So a 99% interval, remember, the higher the confidence level, the wider the interval gets. So this interval got wider, and now it contains the 4, like 3.9 to 6.9, something like that. Okay? So going the other way, I probably had 2/3 to 3/4 of you that got it right. When I flip it around and give you the p-value and start asking about intervals, the wording just gets so sort of confusing that it's hard to sort out. So just when you see a problem like this, notice I use the word when. You see a problem like this on the test, just take your time, take a breath, and read it a couple of times and figure, okay, now think about the confidence interval. Sometimes what I do is if they give me the p-value, say, okay, the confidence interval then has to be outside, and I'll make a confidence interval. It has to not include the 4. And the point here is matching the significance level with the confidence level. That's the key. Now, as a word of caution, this only applies to two-tailed tests. But I won't try to trick you with a one-tailed hypothesis and using a confidence interval. Because to do those, you'd have to split the alpha in half. You'd have to say, do a 90% confidence interval in order to do a 95% one-tailed test. Those two would then match up, but that's above and beyond the Call of Duty for confusion. Okay, so that's just some examples of test questions that get at the idea of the relationship between a confidence interval and a hypothesis test. Okay? So, some misinterpretations of confidence interval, or I'm sorry, of significance tests. First one says, do not reject the null is not the same thing as accept the null. And I've been harping on you about that, right? Why is that the case? Why can you not say, my p-value is bigger than my alpha, therefore I accept the null hypothesis as being true?
You can't accept the exact value because you can't ever be 100% sure that it is that value.
Right. You can never be 100% sure it's that exact value. You can't say for sure. All you can do is say, well, the confidence intervals gives me the values that are plausible, and the null is plausible, so I can't reject it. But I also, so is 6.0 is plausible. So the null is 4. 4 is in there, but so are a lot of other numbers. So you can't say you accept it as being true. You can only say, I fail to reject that it's false. The second one that he lists, this is on page 449. Second one he lists, we've already said, statistical significance does not mean practical significance. The third one, a p-value cannot be interpreted as the probability that the null is true. Now, if you remember, I gave you that as the not quite ready for prime time definition of a p-value. It's the probability that the null hypothesis is true. Technically, that is not a correct statement. It's mathematically not correct because the null hypothesis is a statement about a parameter. Is a parameter a random variable? No, it's a fixed number. So you can't talk about probabilities of things that aren't random. So you can't say it's the probability the null is true. What you can say is it's the probability of getting data like we got if the null is true. That's technically the correct definition. But in terms of making conclusions and deciding whether the cholesterol drug works or whatever it is, then thinking of it that way will never will never cause you to make the wrong conclusion. If you think about it as the probability that the null is true, you'll make the right conclusion from your test. Right? You'll just make some statisticians mad at you for being imprecise. But as a good statistician, the author points that out, that that's not what it really is. The next one says, it is misleading to report results only if they are statistically significant. Why would that be misleading? Think about journal articles. Now, I deal with medical journals most of the time, so think about a medical journal like the New England Journal of Medicine. If they report only the results of trials that have a statistically significant p-value, why would that be misleading?
Because it doesn't include the practical.
Well, no, that's not the point here. That would be a problem. But that's not the point here. What they're saying is they're not even going to publish the paper. If you got a p-value of 0.07, they're not publishing your paper. Right? Suppose there were 100 different researchers all in a race to get their study published to show this new medical breakthrough, to show that it works, right? 100 researchers. Suppose this new medical breakthrough actually doesn't work, so that the null hypothesis is true. How many of those 100 would get a significant p-value just by random chance? In other words, they would make a type 1 error. 5 out of 100. And where'd you get that number?
95%.
From the significance level of 0.05. Remember, that's the probability of a type 1 error. So 5 out of the 100, you would expect would just get lucky with their sample and it would make it look like this new breakthrough works, when in fact it wouldn't. So if the journal only publishes the results from studies that work, they're going to be publishing a lot of type 1 errors. Because 95 of those researchers would never get published. The public would never know that, well, yeah, there was one significant study here, but there was 100 studies that showed it didn't work. Or not showed it didn't work, but didn't find evidence that it worked. Right? So it would be very misleading. So, and this is actually fairly recent development, probably the last 20 years, that medical journals have started to publish, to recognize this and to publish studies that the result was a negative result. We were looking for this to show a difference here, but we didn't find it. That's news, right? And they'll publish that news. The next one is related. It says some tests may be statistically significant just by chance. Okay? So kind of related to what we just did, if we had 100 different researchers studying the same result. Suppose that you are doing a research project and you're looking for causes of some, say causes of heart disease or something like that. So you conduct a big study, you have 30,000 subjects in your study, and you collect all kinds of different variables. Let's say you collect 200 different variables, and you test with a statistical hypothesis test each of those 200 variables. How many of those tests would you expect to look like they're a cause of heart disease, but it's just random chance? Could that happen? Type 1 error again, right? Is it possible to make a type 1 error? For any one test, you have a 5% chance of a type 1 error, and if you do 200 tests, 10. I expect 10 of those variables just to pop up with a significant p-value, even though maybe nothing's going on. Right? So you have to keep that in mind. It's always important to tell your reader how many variables you looked at, not just the ones that are significant. If you publish that, hey, I did this survey and I found 3 variables that seem to be important predictors of heart disease, my first question as a statistician is, okay, but how many did you look at? Because if you looked at 100, then I expect there to be 3 to 5 that are significant. But if you looked at 10 variables and you came up with 3, then I'm more trusting that, hey, maybe you did find something. Okay? The last one in this particular list says, true effects may not be as large as initial estimates reported by the media. What do you suppose he's getting at there?
What was it again? Can you say it again?
It says, true effects may not be as large as initial estimates reported by the media. Let's go back to our 100 researchers that are all conducting the same type study, right? Let's say this time that the null hypothesis is actually false. This thing they're studying does work, right? Who's going to grab the headlines?
Something about the biggest.
The one that got the biggest effect, right? So, they may have all decided that, hey, this works. Some of them are going to say, well, it works a little bit. Some of them are going to say, it works average. Some would get a huge effect. The ones that get a huge effect, if you're a newspaper reporter, you're trying to get readers, which one are you going to report on? The one with the big effect. And this happens quite frequently, actually, in the media. A very good example of this, have you ever heard that eating oatmeal every day reduces your cholesterol? That's a fairly well accepted medical knowledge at this point, that eating oatmeal will reduce your cholesterol. But I remember when the first study came out, they were all excited about it, and this was probably 15 years ago, something like that. And they reported that eating cholesterol could drop your, eating oatmeal could drop your cholesterol by a significant amount. Right? And they started putting it on package labels and all this stuff. Well, researchers started scrambling to duplicate those results. Well, it just so happens that the next study that came out and got published actually had a negative finding and said, we didn't find a difference. We studied oatmeal and we don't find a difference here. Right? Well, then everybody started backtracking. Oh, maybe we were premature in our last report. Turns out, and I remember seeing it on the morning news or whatever, study discredited on oatmeal. Oatmeal does not seem to have an effect. Well, people kept studying it, and what they now agree on is, well, yeah, there is an effect. It's just not near as big as what they first reported on. So the pendulum actually swung both ways. Real far this way, big effect, no effect, some effect, but not a huge effect. So if you eat oatmeal every day to reduce your cholesterol, realize that, well, it's not going to drop it a whole lot. It's actually better than the 2 that I had up there a minute ago, but it's probably more like 10, right? Which is not huge if you're at 300. But if you're at 200, 10 gets you below that magic cutoff, and it's right, it's good for you, and it does other things for you. So, it's not like taking a drug where there's going to be side effects. The only side effect from oatmeal is a dry mouth. Right? So keep that in mind. Whenever somebody makes the press, and they're the first to go to press with it, don't just discount it. Well, I don't believe it. But always have a little healthy dose of skepticism. I'm going to wait until the next study comes out and see what they say, because a lot of times it kind of is slow to zero in on the truth. One study can't be expected to do it all. Okay. Here's a kind of one of the homework problems at the end of the section. It talks about one of the examples that was done in the section. I didn't talk about it, but it was a study that was done on political conservatism and liberalism in America. And they had what's called an ordinal variable. Remember, we talked about ordinal variables as ordered categories. So please rate your degree of conservatism. Suppose that the sample mean was 4.12 and the sample standard deviation was 1.41. And that comes from a sample size of 25, rather than the 4,000 and some that they had when they talked about that example. Find the test statistic, find the p-value, and show that the 95% confidence interval from you was 3.5 to 4.7. So the confidence interval was 3.5 to 4.7. Together with the results from example 11, explain what this illustrates about the effective sample size on the size of the p-value. So the null hypothesis was exactly what I had there that I erased. The mean is 4. Does this confidence interval reject that null hypothesis? No. But if you go back and look at example 11 in this section, they had n equal 4,000 and some, and their p-value was much smaller than 0.05. Their confidence interval shrank, and I don't know what it was, but let's say it was 4.2 to 4.5, where they reject the null hypothesis. What does this example show about sample size and errors in hypothesis tests?
The larger the sample size, the less likely you are to make an error.
Okay. The larger the sample size, less likely to make an error. I'm going to turn it around the other way. The smaller the sample, the more likely you make a type 2 error, because your confidence interval gets too wide. So the larger the sample size, the more likely you are to make a type 2 error. How does that affect the p-value?
Did you say the larger?
Yeah, I think that's something where.
Did I say it wrong?
You said larger.
Thank you.
So it's
The smaller the sample size, the more likely you are to make a type 2 error, because you get larger confidence interval. Right? What does it do to the p-value? Taking a smaller sample, what happens to the p-value? Gets bigger. Right, small sample leads to big confidence intervals and big p-values. Big samples lead to small confidence intervals and small p-values. Okay, here's another a question from the end of the section. This is 956. In 2004, New York Attorney General Eliot Spitzer filed a lawsuit against GlaxoSmithKline Pharmaceutical Company. Who's Eliot Spitzer?
Pervert.
Yeah, the pervert. Yeah, he's the one that got, I think it was some kind of sex scandal, but he got chased out of office. I think he was governor of New York at the time and not attorney general. But this is a true story that it says in 2004 he was attorney general and he filed a lawsuit against GlaxoSmithKline, claiming that the company failed to publish results of one of their studies that showed that an antidepressant drug, Paxil, may make adolescents more likely to commit suicide. Partly as a consequence, editors of 11 medical journals agreed to a new policy to make researchers and companies register all clinical trials when they begin so that negative results cannot be covered up later. Right? So in this case, they're talking about negative results because it has a negative implication for the company. But they found a statistically significant increase in number of suicides, and then they decided not to publish it. Right? That's called publication bias. Right? I don't want this getting out. So what they decided to do is start these, what they call clinical trial registries. So before you ever start the trial, you register the trial so that people know, hey, there's a trial going on, and then later you can ask them, well, tell us what you found, rather than the public never knowing at all that there was such a trial even existed. Right? The question that they're asking is, explain why this controversy relates to the argument that it is misleading to report results only if they are statistically significant. Well, it actually doesn't relate quite directly because they don't tell us whether this increase in suicides was statistically significant or just, some hint of it but not statistically significant. They don't really say. but they're almost hinting that it wasn't statistically significant change in number of suicides, but there did seem to be a trend in that direction. So they argued, well, we're not going to publish it because it wasn't statistically significant. So that's how it relates, is that if you only report the ones that are statistically significant, then there's a lot of good information out there that never reaches the public. Okay? Everybody understand all these things that lead to misinterpretation or misuse of statistical hypothesis testing? As a statistician, when I read a scientific article, what I want to see is I want to see confidence intervals. I want them to say, here's a variable we looked at, here's the confidence interval, and usually it's the effect of this variable on some measure that we're taking, like cholesterol or whatever. What I don't want to see is just a table with the p-values saying this was a significant predictor, this one was not. And the worst is this kind of a table. And these don't happen as much as they used to because they started getting statisticians to review papers before they get published. But what I really hate to see is a variable like age and then just asterisks beside it. And the asterisks in the footnote of the table will say 1 asterisk p is less than 0.10, 2 asterisks p is less than 0.05, and 3 asterisks p is less than 0.001. They don't even tell me what the p-value is, they just say it was significant or it was highly significant or whatever. You're throwing away a lot of information if you do that. Put a confidence interval in there and then I can tell. Right? I can make the decision whether I think it's statistically significant or not. And how strong that is. Okay? Alright, tonight by midnight you have homework over section 9.4, which was the type 1, type 2 error stuff. And then homework over 9.5 will be Wednesday. Friday we'll review. So I will have the review sheet out there soon for you to download and work on. We'll go over that on Friday, and then Monday we'll have a test. See you then.